we will see how algorithms can be designed using iteration. In the last lecture, we saw how algorithms can be designed using recursion. This is the content for the day, a recap and what we will do today. What is a recursive process? What is the difference between a recursive process and iterative process? We are given an algorithmic problem. The algorithmic problem may have been worded very informally. We have to formulate the algorithmic problem very precisely. We call that problem specification or problem statement. Recall that a problem specification includes the precondition of the input to the problem and the postcondition of the output of the problem. In simpler words, we just used input and output. Or what is the input to the problem? What should be the input-output relation that should be solved, that should be satisfied by the algorithm? An algorithmic solution involves the following three steps. 1. Design the algorithm. It starts with an algorithmic idea. 2. We have to construct the algorithm. The way we construct the algorithm should ensure that the algorithm is correct. What do we mean by correctness of an algorithm? If we start execution of the algorithm with an input that satisfies the precondition, the algorithm will terminate with the postcondition satisfied, with the input-output relation satisfied. Then we say that the algorithm has executed correctly or the algorithm is correct. I also pointed out, it is not that we construct the algorithm by trial and error, by an ad hoc method, and then somehow reason or argue that the algorithm is correct. It does the work. It satisfies the specification. Not like that. The way, the manner we construct the algorithm should ensure that the algorithm is correct when we finish constructing that. And finally, we have to analyze the efficiency or the performance of the algorithm. We have not yet discussed what we mean by analysis of the efficiency of the algorithm. But in simple words, we said the efficiency of the algorithm is measured in terms of how long the algorithm takes to run to completion. And then how much memory space is required by the algorithm to run to completion. So we are interested in analyzing both running time and memory space. Very often we are interested or we do only running time. So solving a problem with an algorithm involves design the algorithmic idea, prove the correctness of the algorithm constructed, and analyze the running time of the algorithm. Then in the last lecture, we introduced a very powerful technique for solving algorithmic problems. It is called recursion. The recursive problem solving involves, every recursive problem solving involves these three phases. 1, deconstruct the input given to the algorithm into a smaller input and an element. Then make a recursive call to the algorithm to solve the same problem with a smaller input. That recursive call will return a solution to the smaller input. then the call to the algorithm should construct a solution from the sub-solutions. This problem with a given input is called an instance. A problem with a smaller input is called a sub-instance. Therefore, we may also say any recursive problem solving involves one, deconstruct the instance into a sub-instance and an element. Two, by a recursive call, solve the sub-instance. And three, construct a solution to the instance from the sub-solution. Note that we didn't say that the instance has to be deconstructed into only one sub-instance. The instance can be deconstructed into one or more sub-instances. There may be just one sub-instance or two sub-instances or even more than that. In that case, the solution is to be constructed from the sub-solutions of all the sub-instances. When we design a recursive algorithm, we have to take care of two cases. One is called base case, the other is called recursion stub. Every recursive algorithm should have at least one base case. If there is no base case, a recursive algorithm will never terminate. We use the phrase, if there is no base case, a recursive algorithm will never bottom out. Every recursive algorithm should also have a recursion stub. The recursion step makes a call to the same algorithm with one difference. The call is given an input. The recursive call is given an input which is strictly smaller in size. We emphasize the word strictly. The input size to the recursive call should be strictly smaller than the input size to the call. Whenever we design a recursive algorithm, we have to take care, we have to ensure these two conditions. There is at least one base case, and in the recursion step, the input size is strictly smaller than the input size given to the original problem. Every recursive algorithm, when it is executed, generates a recursive process. But I said, in order to design a recursive algorithm, it is not necessary to trace a recursive process. That is a good news. In fact, whenever we have to design a recursive algorithm, if we are bent on tracing and visualizing the recursive process, that would become a waste of time. Tracing and visualizing the recursive process does not add anything more to solving the problem. It is an unnecessary thing. But sometimes it is necessary to trace the recursive process. I will tell you when. And then we made a very important observation. There is a close relationship between recursion and iteration. Both are repetitive. Recursion repeats the same operations only with different inputs. Smaller input, still smaller input, still smaller input, and so on until the input size becomes 0 or 1, until it becomes trivial. Iteration also is repetitive. It repeats the same set of operations repeatedly. So, in this sense, recursion is similar to iteration. Both repeatedly execute the same set of operations. However, there is a very important difference between recursion and iteration. At least one difference we have already noted. Whereas in recursion, an instance can be decomposed, can be broken, can be deconstructed into one or more sub-instances. In iteration, an instance of a problem can be broken into only one sub-instance. It is very important. And there are other differences, but at least this difference we already know. In this lecture, we will understand clearly the difference between recursive process and iterative process. And then the link between recursion and iteration is called tail recursion. tail recursion is iteration. And then finally we will say, instead of coming to an iterative algorithm through a recursive algorithm, practically it is useful to come to the iterative algorithm straight away. And whenever we design an iterative algorithm, an idea called loop invariant is useful to design and construct the algorithm correctly. Okay, so that is the work for the day. The point is, recursion is more expressive than iteration. But a subset of problems which can be solved by recursive algorithms can also be solved by iterative algorithms. More often than not, designing and constructing an iterative algorithm is easier. Therefore, we treat iterative algorithm in its own right. Instead of treating iterative technique as a subset of recursive, instead of treating iteration as a specialization of recursion, we will treat them as two different techniques. Okay, either the problem is solved using recursion or it can be solved using iteration. This we have already seen. Last lecture we saw we are given a list as the input. The output should be the length of the list. How a recursive process unfolds or evolves. Let us go on to the difference between recursive process and iterative process. I will illustrate the difference between recursive process and iterative process with the help of list. That does not mean recursion or iteration works only with lists. It can be a list. The input may be a list, or the input may be an array, or the input may be a tree, or the input may be a graph, or it may be a humble number. It is not as humble as it appears to be. Especially, I will be using list. You should know the difference between list and array. I can ask a question and wait for the answer, but it is not very deep. Therefore, let me answer and keep going. An array has a fixed size. If you create an array with n items, throughout the execution of the algorithm or the program, the array will continue to have only n items. Whereas a list can have varying number of items. The size of a list can be varying, whereas size of an array is fixed. People may use the stylish word, oh, array is static data structure and list is a dynamic data structure. It's okay if you use those words. For me, the most important thing, it is possible to vary the size of a list, whereas size of an array is fixed. A list can grow or shrink. We can add items to a list, delete items from a list, concatenate two lists, and so on. We don't do such operations. Therefore, it is easier to deal with lists than with array. A question for thought to those of you who have already been exposed to programming in Python. What Python calls a list, is it a list or an array? Can I wait for an answer? What is called a list in Python? Is it a list or an array?
It's a list.
It's a list, sir.
List.
Okay.
It's a list, sir.
It is a list because the size can be varying. Is that
Yes, sir.
okay? That is one difference.
And many different elements can be elements need not be of the same type.
Elements need not be of the same type.
Yes, sir.
Oh, is that a part of the definition of list? Element in a list, elements can be of different types. My understanding
I,
is that a list and an array does not differ in that. In an array, all elements should be of the same type. In a
yes, sir.
list also, in a list also, all elements should be of the same type. That is my understanding.
Oh,
Am I right?
I thought like list can have different types of elements as well.
Check that and get
Yes,
back
sir.
to
Yes,
me.
sir. Yes, sir.
Okay. However, there is a very important difference. In an array, suppose this is item 1, item 3, 2, item 3, and so on, item n. Suppose this is item I. The time it takes to access item 1 or the time it takes to access item 2 or the time it takes to access item I or the time it takes to access item n. Are they all the same or do they differ?
Same.
They are the same, sir.
They are the same. So it takes the same time to access item n as it takes to access item 1, right?
Yes,
Yes,
sir.
sir.
Okay.
Sir.
So
Sir,
yeah.
I just checked for the difference between list and an array, sir. A
Mhm.
list in Python can contain elements of different data types.
Okay. Oh, I have no doubt about that. I know a Python list can have elements of different types. I'm asking in data structures, how do you define a list? Do you define a list? Do you
Yes,
define
sir.
a list to be to contain items of the same type, or you allow items of different types in
Different
data?
types, sir. Array is the
Uh,
one which needs to contain elements of same data type.
okay. Uh, maybe I differ. What is your reference book for data structure?
Uh, I just checked Geeks for Geeks, sir.
What is your reference book, by the way?
Uh, I think in first semester, Vinod sir told us this. I don't remember exactly.
No, no, no. In third semester, you study data structures, right? May I know
Uh, yes, sir.
which is your
We
reference
didn't
book?
have a reference book. I mean, like I didn't use a reference book.
Okay. Here is my commandment.
Okay, sir.
Woe unto a man who reads but one book. You should read at least two books. If you do not even read one book, then double woe. Okay. If you have
Yes,
not
sir.
read Alan Weiss, you should read that.
Yes, sir.
Mark Alan. If you have time for only one book for data structures, it is Mark Alan Weiss. Next time someone asks, what is your, I'm sorry. Next time someone asks, what is your book for data structure? I mean, I don't want my students to say, oh, by the way, please mute. Oh, yours is okay.
Yeah.
I don't
Yes,
want my
sir.
students to answer, oh, we didn't read a book. It is Wikipedia. You should have an answer. All right.
Yes, sir.
Uh, I almost dare to say that and in an array, all items are of the same type. In a list, all items are of the same type. I am shouting from the rooftop. In a list, all items are of the same type. I'm sorry, I have to shout.
Okay, sir. Understood.
However, a Python list can have items of different types. But Python list is a peculiar animal. Python list is not what we call a list in data structure. I am coming to that point. In an array, the time taken to access item 1 is equal to the time taken to access item n. In fact, regardless of the index of the item, every item can be accessed in the same amount of time. We say that the access time is constant in an array regardless of the index, the position of the item. I think that is clear. In an array, the access time of any item is the same, independent of the index or position of the time. We call that direct access or random access. Here is the question, maybe in the cat. What is direct access? What is random access? Whereas in a list, item at index 1, 2, 3, and so on. Let's say there are n items. Here you cannot say the same thing. It takes, to access item 2, we have to traverse item 1. You have to traverse items 1 and 2 to access item 3. You have to traverse item 1, 2, 3, and so on up to I minus 1 to access I minus 1th item. You have to traverse 1, 2, 3, and so on up to n minus 1th item to access n. Therefore, the access time of items in a list depends on their position. So I point out two differences between an array and a list. The first and a simple difference is an array has fixed size, while a list the list can have varying size. But that is by the way. The most important is in the access time. The second difference, in an array, access time is a constant for all the items. In a list, access time varies depending upon the position. Therefore, we say it is sequential access.
Sir, I have a doubt, sir.
Yeah.
When we talk about list, sir, is it exclusively linked list?
That is how all the programming languages implement lists, except
Oh.
Python.
Okay, sir.
Okay.
Yes, sir.
So one is the size, the other is the access time. I have spent more time on this matter, but this is useful for your programming in general. In Python, however, the access time is the same for all the elements. A Python list is not a linked list. The time it takes to access item 1 or item n is all the same. So therefore I say Python list is a strange animal. It can vary in size like a list, but it has direct access like an array. The items may be of different types like a tuple, like a record. Do you understand what I mean? When I say, I'm not playing with words, when I say it's a peculiar animal, it acts like an array, it acts like a list, it acts like a record or a structure or a tuple. Okay, it's a very powerful data structure, but it is not one single data structure, such as array or list or tuple. I hope you get this point clearly. All right. In a list, there are only three basic operations. A list is constructed by prepending an element to a list. Suppose you have an empty list. Okay, I can prepend 1. Let me denote the prepend operation by this colon for the time being. Not in Python, just for convenience. So 1 colon empty list means prepend item 1 or element 1 to empty list and you get 1. Suppose I want to prepend item 2 to a list consisting of only one item. After prepending, you will get 2, 1. Suppose I want to prepend 3 to list containing 2, 1. I get 3, 2, 1. So that's prepend. Remember, U is an element. V is a list. In Python, you may do it like this. In Python, plus is a concat operator. In order to concat, both should be lists. V is a list, U is an element. You can convert element U into a list by bracketing it. Okay. The first element of a list is called head of the list. The remaining elements is called the tail of the list. Tail of a list is a list itself, is another list. Head of a list is an element. In Python, if V is a list, you can V at 0 is the head of the list. V at 1 to the end is the tail of the list. Remember, Python is not a pure list as in the case of other programming languages. But since Python is the programming language that you are using, I am drawing a parallel between the list operations and the Python list operations. So there are only 3 basic operations. What is the connection between prepend, head and tail? Suppose you take the head of a list and prepend it to the tail of the list, you will get the list itself. So the 2 operations, head and tail, are used to take a list apart, to deconstruct the list. Prepend is used to construct a list. Prepend is the inverse or complementary operation for head and tail. Head and tail to construct a list from a smaller list and an element. Sorry, head and tail are used to take apart a list into tail and head and tail. Prepend is used to construct a list. Okay. Now for a simple operation, we want to append an element U to a list V. Prepend adds an element at the front of a list. Append adds an element at the rear of the list. Input is an element U and a list V. Output is a new list, which is equivalent to U added at the rear of the V, rear of the list V. Mark my words very carefully. I did not simply say U added at the rear of V. I am not changing V itself. It is not a mutation of V. From V and U, I construct a new list. That new list is equivalent to, if you have added U at the rear of V, how will that look like? That list is the new list created. Okay. How will we write a recursive algorithm? What is the base case? Consider this example. Append 4 to the list 1, 2, 3. That means I want to get 1, 2, 3, 4. But we have only one operation. We have only 3 operations: head, tail, and prepend. So how can we do that? We can take the tail of the list, and this is the, we can take the head and the tail. Appending 4 to 1, 2, 3 is equivalent to appending 4 to 2, 3 and then prepending 1. Hope you get that. 1 prepend, instead of append to write in full, I have just written A. Append 4 to 2, 3. This is equivalent to append 4 to 3, the list consisting of 3, and to that you prepend 2. Okay, what is this? Deconstruct 3 to 3 and empty list. So this is equivalent to append 4 to empty list. This is a base case. How do we append an element to an empty list? Just a singleton. Yeah, just a singleton thing. Yeah. 4 is appended to empty list means a list consisting of just 4. So that's the I call sequence. Now for the return sequence or return journey. Okay, this is one recursive call. This is a call. It has made one recursive call. Until the recursive call returns, this call is pending. Okay. This operation, this construction operation is pending until this recursive call A4, append 4 to 2, 3 returns. Similarly, to prepend A4 list 3 is also pending. All right. Now in the return journey, first here, it is the operation 3 prepend is pending. Therefore, here 3 is prepended to 4 and we get the list consisting of 3, 4. This is 1, call 2, call 3, call 4. So call 4 is completed. In call 3, what is the pending operation? 2 needs to be prepended to the result. And therefore, in call 3, 2 is prepended to 3, 4, resulting in 2, 3, 4. In call 2, what is the pending construction operation? 1 needs to be prepended, and therefore here 1 is prepended to 2, 3, 4, and we get 1, 2, 3. And this is the original call. We have already got the result. Therefore, 1, 2, 3, 4 is returned. If you write the algorithm, we have to identify base case and recursion step. What is the base case? If the list is
Empty.
yeah, v is equal to empty, then return list consisting of a single item u. This is the base case. In the recursion step, the given input is v. We have to deconstruct that into a smaller input. What is a smaller input? V at 1 to the end. V consists of V at 0, V at 1, V at 2, and so on up to V at n minus 1, whatever it is. I'm using Python notation. So I have deconstructed V to V at 0, a single element, and V at 1 colon end, 1 to the end. And we say that this is a call. This is a recursive call. And I said in the recursive call, the input size should be strictly smaller than input size to the call. What is the input size to the call? Size of V. What is the input size to the recursive call? Size of V at 1 to the end. Are you sure the size of V at 1 to the end is strictly smaller than the size of V?
Yes.
Yes, because we have removed V at 0.
One element. Yeah.
It is 1 element less. So we have reduced append u to v to append u to v at 1 to the end. After we get the result of the recursive call, the value of the recursive call, we construct the solution by prepending v at 0. That's all. Now for how long it takes, how long the algorithm takes to run to completion. Okay. This we call analyzing the running time. Let me denote the size of the input by n. If input size n is equal to 0, how much time it takes? I will say some constant time. If n is equal to 0, to construct and return the list consisting of u alone will take a constant time. I will, instead of writing a constant time, I will just write, okay, 1 unit of time, something like that. More interestingly and more importantly, suppose n is not equal to 0. How long it takes? Here input size is n, here input size is n minus 1. If I denote the running time of append u to v as t of n, I can denote this by t of n minus 1. The running time of append u to v, because v size is n, I denote that by t of n. Because v 1 to the n size is n minus 1, the running time of append u comma v 1 to the end is t of n minus 1. What is the connection? What is the relationship between t of n and t of n minus 1? After I have spent t of n minus 1 to calculate append u comma v from 1 to the end, I have to do some constant work. Prepending v at 0 to the result is a constant amount of time. Constant amount of time I always write as 1. Therefore, the time taken is 1 plus t to the t of n minus 1. Here is it is. The running time of this algorithm is t of n is equal to, there are two cases. If n is equal to 0, the running time is 1. Otherwise, if n is greater than 0, the running time is, sorry, this is wrong, t n minus 1. Remember, I am not interested in the wall clock time. More on this later. Now, this is an example of a recurrence relation. This does not give me an idea. What would actually be t of n? Would t of n be a constant time? Even if n increases, the size of the input increases, will t of n be a constant? Or is it a linear time? If n increases, t of n, the running time, also increases linearly? Or is it a quadratic time? If the input size n increases, the running time increases by square? What is really the situation? In order to find out how t of n varies, as n varies, we have to solve this recurrence relation. This is not a great solution, but one way of doing that. T of n is equal to 1 plus t of n minus 1. 1 plus t of n minus 1 is 1 plus t of n minus 2. 1 plus t of n minus 2 is 1 plus t of n minus 3. And so on. Eventually, I will get n times 1 plus 1 plus 1 plus and so on plus 1 plus t of 0. So this is n. T of 0 by definition is 1, and therefore the running time is n plus 1. If there are, let's say, 10 items in the list, to append a new item takes 10 units of work because we have to traverse all the 10 items. If there are 100 items in the list, we have to traverse all the 100 items to append a new item, and so on. Therefore, we say it is linear. Linear time. What is the meaning of linear time? As input size increases, the running time increases linearly. Oh, I can approximate, just leave out this plus 1 and simply say n. This notation is called big O notation. More on this in the maybe in the next two classes. Big O notation. Let's say I am crudely approximating. Instead of saying n plus 1, I say it is big O of n. Homework. Write an algorithm to concatenate two lists. Algorithm concatenate u comma v, input two lists u and v. Output should be a new list in which elements of u are added in front of v. Okay. Example. 5, 2, 3, append it to 1, 7. The result should be 5, 2, 3, 1, 7. Okay. Write an algorithm. For example input, trace your algorithm. Do all those things. Right? Complete this algorithm. Trace the recursive process. For an example. And 3, what is the running time? Not much different from append, but do that. Now let us go on to another problem. Reverse a list. Algorithm reverse a list A. Input is a list A. Output is the reverse of A. For example, if input is 1, 2, 3, 4, output should be 4, 3, 2, 1. Suppose input is empty, what should be the output? Empty. Let us write a simple, straightforward recursive algorithm. The base case is if A is empty, then return empty. How will you reverse if it is non-empty? I deconstruct this into head and tail. This is A at 0 is the head in Python notation. A at 1 to the end is the tail. Okay. Reverse 2, 3, 4. That is reverse the tail. And where will we put the head? After reversing 2, 3, 4, you will get the answer.
Append the head.
Right. You will get the answer 4, 3, 2, and we have to append that. Therefore, I write reverse A at 1 to end. This is reverse the tail of the list. And then this is append the head. If it is Python, be careful to put a bracket here. I am not using strictly Python notation. So this is a complete algorithm. Let us trace it. Reverse 1, 2, 3. We have deconstructed to reverse 2, 3, 4, append 1. That would be deconstructed to reverse 3, 4, append 2. That would be deconstructed to reverse 4, append 3. That would be deconstructed to reverse empty list, append 4. This is a base case. Reverse empty list is empty. Now is the time to do the pending operation. What is the pending operation here? The result of reverse of 4, append 3. Therefore, it is empty list appended to 4. All right, okay, here. Empty list is the result. Append 4, we get list consisting of 4. And here this is the pending operation. Now do the pending operation. That would be 4, 3. The result of list 4, append 3 will be 4, 3. So 4, 3 will be returned here. What is the pending operation here? The construct append 2. Therefore, here the append 2 will be done, resulting in 4, 3, 2. What is the pending operation? Pending construction operation here. Result of 2, 3, 4, which is 4, 3, 2, append 1. Okay, giving the result 4, 3, 2, 1. And this is the original call. It is given the result 4, 3, 2, 1. Look at that. In the call sequence, the input is 1, 2, 3, 4. To the recursive call, the input size is strictly smaller. Here the input size is 4, input size is 3, input size is 2, input size is 1, input size is 0. So in the call sequence, the input is deconstructed into a smaller input. In the return sequence, we are constructing a solution. There is a pending operation, pending construction operation, and we are doing that. Can we analyze the running time of the algorithm? T of n, T for time. If the size is n, for the base case, the input size is 0, it will take a constant time. That's all. We can never say 0 time, it will take a constant time. So this is done. Otherwise, if n is greater than 0, okay, if this is the time for T of n, here, the input size is just 1 less than the original size. Therefore, this is T of n minus 1. But very important question. How long will that take to do this operation? Append A at 0 to the result of this reverse. Can you answer?
N time.
Okay. Can it be done in constant time? It cannot be.
Or
In order
no,
to
sir.
append A at
N.
0 to reverse, if reverse has n minus 1 elements, we have to traverse all the n minus 1 elements, and only then we can append A at 0. Okay, and therefore, okay, this should be n minus 1. It doesn't matter. So this is the recurrence relation for the running time. Can you take 1 minute and solve it as we did for append? You expand T of n minus 1, then you will get T of n minus 2. Expand T of n minus 2, expand T of n minus 3 until you get T of 0. And can you give me the result? You can take 1 minute, all of you.
We get big O of n square, sir.
What do you get?
Big
No,
O of n
without big
square.
O. No, without big O.
Without big O.
N minus 1, n minus 2,
N
and
into
so
n
on,
minus 1.
plus 1. Okay. I don't know whether you get one more 1. Doesn't matter. Suppose you consider the whole thing, it will be n minus 1 times n by 2 plus 1. This would be n squared by 2 minus n by 2 plus 1. Okay, generally what I will do is ignore these smaller terms and ignore this factor, and you will say this is big O of n squared. The time is almost up, but let me ask this question. So, if there are 10 items, okay, if there are 1 item, it takes 1 unit of time to reverse. If there are 10 items, it takes 100
100.
units of time. If it 100 items, it takes 10,000. But is the reverse operation so inefficient? If there are 10 items in an array, in a list, will that really take 100? Do I need to access the elements 100 times? Can we do it better?
Sir, maybe we can start from the end and directly print it, sir. Rather than doing it from the front end. Can we do it from the back end, sir?
If it is an array, the direction does not matter, because in an array has direct access, you can traverse the elements of the array 1, 2, 3, 4 or 4, 3, 2, 1. If it is a list, a pure list, then you can access the items of the list only in one order, sequential. First 1, then 2, then 3, then 4. You don't have the luxury of traversing in the opposite direction.
Yes, sir.
I will share with you the idea. It is the same tracing of the recursive process. For the first call, reverse 1, 2, 3, 4. The next call is reverse 2, 3, 4. The pending construction is plus 1. The next call is reverse 3, 4 plus 2, the pending construction. This call does not see this plus 1 at all. This is a historical input. This call handle only, it sees only 1, 2, 3, 4, deconstructs to 2, 3, 4, and then 1. This call sees only 2, 3, 4. Though I have shown it here, this call sees only 4 and 3. Plus 2, I mean concatenate up and 2 and up and 1 are in the past history. And this sees only 4. When it returns empty, concatenate 4 will be list consisting of 4. When that returns 4 append 3, 4 comma 3. When that returns 4, 4 comma 3 append 2 and so on. So whatever I have shown here in red is historical input. The recursive call does not see that. Think about that. Okay. But look at this question. To empty list, append 4, append 3, append 2, append 1. Is this not the same as if to an empty list, I say prepend 1, prepend 2, prepend 3, prepend 4? Yes. So let me start here. Instead of calling 1, 2, 3, 4, I call with 1, 2, 3, 4 and also an empty list. It deconstructs 1, 2, 3, 4 to 2, 3, 4 and 1. Instead of waiting for the return journey to append 1, let me immediately prepend 1 to the empty list. In the next 2, 3, 4 is deconstructed to 3, 4 and 2. Prepend the 2. Then 3, 4 is deconstructed to 4, 3. Prepend 3 and so on. So instead of appending them in this order, prepend them in this order. Then I can arrive at a different algorithm. This was the algorithm that we have already seen. Now for this algorithm, look at that. We have the list. We also have a partial solution. Okay. If A is equal to empty list, then return the solution. When A is equal to empty, the entire input has become the historical input. R is a partial solution to the historical input. When the entire input is a historical input, the partial solution is the solution and therefore return that. Otherwise, what would you do? Just as we did here, we are still deconstructing that into head and tail. This is head and this is tail. A at 0 is the head, A at 1 to the end is the tail. But instead of calling this way, we have already defined extend the partial solution. The partial solution is R. The head A at 0 is prepended to R, thereby growing the partial solution. And the remaining input is reduced to A at 1 to the end. Okay. Homework. Compare the running time of this algorithm versus this algorithm. This is the trace of the first algorithm, A1. This is the trace of the second algorithm. The main difference you will notice is that in the first algorithm, in the return journey, a pending operation is performed. This is performed. This is performed. This is performed. This is performed. Whereas in this algorithm, in the return journey, there is no pending operation. Here is the result. In the previous recursive call, nothing is done. In the base case, 4, 3, 2, 1 is returned. The previous call also returns 4, 3, 2, 1. The previous call also returns 4, 3, 2, 1. The previous call also returns 4, 3, 2, 1. And the call returns 4, 3, 2, 1. And this is known as tail recursion. It's a high sounding word for iteration.